The conservation of linear momentum is a useful tool in describing translational collisions. In the same way, the conservation of angular momentum is a useful tool in describing collisions that involve rotation. To fully consider collisions, we'll need to return to our equations. Remember that angular momentum is equal to rotational inertia multiplied by angular velocity. For extended objects, hoops, spheres, cylinders, we'll continue to use the same equations that we have to describe their rotational inertia. Remember that all of these equations are proportional to mass times radius squared. Point masses can sometimes behave differently. Remember that a point mass means a small mass that's revolving around a center point. The rotational inertia of such objects is still equal to mass times radius squared, which means the angular momentum is mass times radius squared times the angular velocity. But sometimes we'll run into situations where it's helpful to write this equation in terms of the tangential velocity of the object instead of the angular velocity. Remember that tangential velocity is equal to the radius multiplied by the angular velocity. That's our bridge equation. If we expand the equation on the right, we can write this as m r omega, and r omega is equal to tangential velocity. This gives us an equation for angular momentum that's proportional to the tangential velocity instead of the angular velocity. We'll come across some examples where this comes in handy. Let's consider two examples. In the first example, let's say we have a rotating turntable. It has a rotational inertia I1 and is initially rotating with a rotational velocity of omega 0. Now let's say we have a non-rotating plate that has half of the rotational inertia of the first plate. So I2 is equal to 1/2 of I1, and omega of that plate is equal to 0. If we were to drop this non-rotating plate onto the rotating plate and they collided inelastically, we would end up with both plates rotating with a new angular velocity. Let's look at how we could use the equations for angular momentum to figure out what this new angular velocity is in terms of the original angular velocity, omega 0. We'll start this problem by setting the sum of the angular momentum at the beginning equal to the sum of the angular momentum after the collision. On the left-hand side, we have two different objects. The small plate has a rotational inertia of I1, 1/2 I1, times 0. The larger turntable has an inertia of I1 multiplied by omega 0. On the right-hand side, once this plate falls down and lands on the turntable, the rotational inertia on this side can be found by just adding these two rotational inertias together. So we have 1/2 I1 plus I1, which is equal to 3/2 I1. So I'll write that over here. Our rotational inertia is 3/2 I1, and here's our angular velocity that we are trying to solve for. All right, anything times 0 is 0, that cancels out. I can also divide both sides by I1, and this cancels out with that. And I'm gonna write this so we can see how it's simplified. Omega 0 equals 3/2 omega, but I actually want to solve for omega. So I'm gonna multiply by 2, I'm gonna divide by 3, and I find out that omega is equal to 2/3 omega 0, or that the final angular velocity is 2/3 of the original angular velocity. In our second example, let's consider a child running towards a merry-go-round. Let's say that the merry-go-round has a rotational inertia of 400 kilogram meters squared and is initially not rotating, so omega 0 equals 0. And let's say the radius of the merry-go-round is 2 meters. Maybe our child has a mass of 30 kilograms and is initially running with a velocity of 3 meters per second. After the child jumps onto the merry-go-round, how fast will it be rotating? That means, what will our final rotational velocity be given these initial conditions? We will again start this solution with the conservation of angular momentum. So the sum of the momentum before the child jumps on the merry-go-round is equal to the sum of the momentum after they jump on the merry-go-round. Before the child jumps on the merry-go-round, we have two separate objects. So we will have to find the angular momentum of the merry-go-round, call that MGR, and we will have to find the angular momentum of the child. Those two added together will be equal to the angular momentum of the child on the merry-go-round. So let's look at each of those separately. The initial momentum of the merry-go-round is easy because it's not moving. It has an initial speed of 0, so this is going to be equal to 0. As we look to find the angular momentum of the child, we don't really care what his angular momentum is over here. We only care right as he's making contact with the merry-go-round, right as he's jumping on. So in that case, we are going to use the expression that the angular momentum is the mass times the radius times the velocity. So this child has a mass of 30, the radius of the merry-go-round is 2, and the speed is 3 meters per second. 30 times 2 is 60, 60 times 3 is 180 kilogram meters squared per second. All right, after the child is on the merry-go-round and the whole thing is rotating, this angular momentum will be equal to the rotational inertia of the child plus the merry-go-round multiplied by the angular velocity. And this is what we're really trying to solve for. So just like in the previous example, once the child has jumped onto the merry-go-round, they're moving together, but we can add up their their rotational inertias to get the total rotational inertia. So to find I here, we'll take the rotational inertia of the merry-go-round by itself, and then we'll add to that the rotational inertia if we just had the child. And his inertia would be equal to mr squared. Okay, so 400 plus the mass of the child is 30, the radius of the merry-go-round is 2. Okay, 2 squared is 4, 4 times 30 is 120, 120 plus 400 is 520. And that's the rotational inertia, so kilogram meters squared. Okay, so let's put this all together into an equation. The initial angular momentum over here is 0 plus 180, and the angular momentum over here is the inertia 520 multiplied by that final angular velocity that we want to solve for. Okay, so we'll divide by 520. (180) divided by 520. And there we have our angular velocity. Omega is equal to 0.346 radians per second. In summary, we've learned a lot about angular momentum. We've talked about its equation, L equals I omega, and we've talked about what it means that angular momentum is conserved, both in amount and in direction. And in doing so, we've considered 3 types of examples. Single spinning objects like ice skaters who change their inertia, which then changes their rotational velocity. We've looked at what it means for the direction of angular momentum to be conserved and talked about tops and gyroscopes that continue to spin upright. And we've looked at collisions and how the conservation of angular momentum helps us solve problems that involve collisions. I hope this has been helpful. Happy physicsing!